Well, hello everybody, Dave here, and today we're going to take a look at some complex circuit problems, and through that we're going to discuss internal resistance and the difference between terminal voltage and EMF. So when we get into complex circuits, the basic strategy is going to be to take the complex circuit, find the equivalent resistance, and then determine the total resistance of the system by which we can determine whatever we have to find. So if you look at a circuit like this, we can see that we have an 80 ohm resistor in series with this 100 ohm and 50 ohm resistor that are in parallel to each other. The first thing I want you to recognize is the direction of the current. The current is going to travel from south to north, from the negative to positive in this northerly direction. Conventional current is always going to be the motion of a positive charge. So when we think of the current traveling through, then we're going to have this in a clockwise loop. Now, if we have to determine the equivalent resistance, the first thing we have to do is figure out, well, how much resistance is in the parallel structure. And so you can see that we have calculated specifically the parallel resistance as 1 over 100 plus 1 over 50. Notice how we haven't dealt with the 80 ohm resistor yet. And what we end up with is 33.3 ohms. Again, this satisfies the idea that the equivalent resistance in parallel is always going to be less than the individual resistors in parallel. Now that we have this equivalent resistance, we can imagine this circuit as being two resistors in series. Once we understand this, we know that the resistance adds up in series, and so we can find the equivalent resistance by taking 80 and adding it to 33.3 to get 113.3 ohms. The extension to this now would be, if we knew something about the current or the voltage, we could find the other quantity. So this strategy for complex circuits is going to be one that I generally want you to do, because it takes complex circuits and it makes them far more simple. So now that we have the equivalent resistance, we can find the current if we're told that the potential difference is 120 volts. And we can simply use Ohm's Law to do so. And so given that, we know that the current is going to be 1.06 amps. With the current now, we can determine the potential drop on the 80 ohm resistor, because we know that the current across the 80 ohm resistor is going to be the total current, and the resistance is already listed to give us a value of 84.8 volts. Now, something important to recognize there is if we want to find the voltage across the parallel components now, we actually have to take the difference of 120 and 84.8. And that's exactly what we do here. We recognize the fact that if 84.8 volts is used on the 80 ohm resistor, that only leaves 35.2 volts, which is going to be across both parallel branches of this circuit. And so now if we want to find the current across the 100 ohm resistor, we have to use the 35.2 volts and use Ohm's law to determine that there is 0.352 amps across that branch. To find the current across the 50 ohm resistor, we use exactly the same idea. The neat part about circuits is, if you've done this correctly, we know that the total current should be the sum of the currents in the parallel branches. And in this case, if we take those two currents and add them up, we indeed get 1.06 amps. So these are neat little physics puzzles that we can do, and the only way to make these more challenging is to remove more and more information to make you really figure out, how do I apply these circuit laws in dealing with these circuits. The last thing I want to bring up is what happens when we actually consider the internal resistance of a battery. So if you look at the diagram on the right, you can imagine the dashed line to be the outside casing of the battery. And inside we can represent it according to these two devices, a power supply and a small resistor, which we'll label as lowercase r. Now, the power supply is going to produce a voltage that is the ideal voltage for that given supply. But what's going to happen is, once this voltage is generated and it produces a current that leaves the power supply, it's going to hit that small resistor and have to drop some of its energy on that resistor, which means that if we hooked up a voltmeter to this battery across terminal A and B, what we would read is not going to be this ideal EMF. It's going to be the result of whatever we had in the EMF subtract whatever voltage is dropped on the internal resistor. And so the equation of VT is equal to epsilon minus IR is exactly what that's trying to represent, is that the actual reading on a voltmeter is going to be whatever the ideal voltage is for that power supply, subtract whatever voltage is dropped on that internal resistor. Now, one thing I do want to let you know of is when you are dealing with circuit problems like this, you can still treat this like a circuit as if the dash box doesn't exist. What's going to happen though are questions are going to ask you for EMF or terminal voltage. But as far as the actual use of Kirchhoff's law is concerned, you can use any methodology that works for you as if that dash line is not there. There's one more thing I'd like to do with this equation. I'd like to substitute in for terminal voltage using Ohm's law. And we know that terminal voltage should be equal to the total current times the total resistance. We also know that the total current is across that internal resistor, which means that I can rearrange this equation now and solve for the total current as being epsilon over the sum of the total resistance plus the internal resistance. Now, I can do something mathematically challenging, and I can multiply the denominator up to the left-hand side, and then I can multiply both sides by the total current. And what I end up with is the equation that you see below. Now that looks complex unless you remember that when we took the equation for power and we substituted in Ohm's law, what we ended up with is I squared R. And so what this equation actually tells us is that the power associated with the power supply is equal to the sum of the powers on each of the digital devices. So this is exceptionally useful when we're dealing with complex circuits, because when we have light bulbs in series or in parallel, or resistors in series or in parallel, when it comes down to power, we simply need to know how much power does the power supply have and how much power is being used by each individual digital device. This is also the way that you're going to be able to describe the brightness of light bulbs, because the basic understanding is going to be the more power that is used by the light bulb, the brighter it's going to be. And so I encourage you strongly when you're dealing with practice problems that you essentially deal with three types. The types where it is basic, parallel, and series circuits, so that you can just brush up on your Kirchhoff's laws. Then move on to the more complex circuits where we have devices both in series and parallel, so that you can really exploit the use of Kirchhoff's laws and understanding what happens to the current, voltage, and resistance in those cases. And then on a more conceptual end, I want you to understand when we replace resistors with light bulbs, what happens to the brightness of these light bulbs when the circuit changes. And the basic understanding again is that the more power that's used by a light bulb, the brighter it's going to be. So let's do a problem that applies this principle now. We can see that we have a circuit here with a dash box around a power supply and a resistor. That tells us that the principles of terminal voltage and EMF are going to apply. We also see two light bulbs and a wire that connects across the circuit, and there's a switch on that wire, and you'll notice that it is connected in such a way that it would affect lamp B, which is going to be important later on. And so we see in the question that the switch is initially open, and we have a current of 1.5 amps flowing in the circuit. And the question is, what is the internal resistance of the battery? Well, we know from our previous studies of power that if we know the current of the circuit and we know the power dissipated by the light bulb, that we can actually find the voltage drop on that device. So you can see that the first two calculations are to find the voltage drops on lamp A and lamp B. Because we were told that each light bulb dissipates 5 watts, it's not surprising that it's the same. From there we can apply Kirchhoff's law of voltages in series, which tells us that the total voltage, which in this case is going to be our 8 volts, is equal to the sum of the voltage drops on each of the devices. Now it seems weird because we have this dash box around it, but remember that even though we're dealing with this concept of EMF versus terminal voltage, we can still apply all of Kirchhoff's laws as if that dashed box didn't exist. And so when that's the case, we know that the sum of the voltages, including the voltage drop on the internal resistance, should add up to 8 volts. From that, we can find that the voltage drop on the internal resistor is 1.34 volts. From there, we can simply apply Ohm's law to find out that the internal resistance is 0.89 ohms. So you can see that all of the lessons that you've had in circuits now are being used in this circuit right here. Part B now has us close the switch and ask the question of what happens to the brightness of lamp A and the magnitude of the terminal voltage. This is a classic conceptual question that teachers love to ask because it makes us understand the behavior of the current in a circuit and why this switch was so important. Well, with the switch closed, we've now given it a path of no resistance. You'll remember when we studied current that we said that current will always travel down the path of least resistance, and we will also assume that all wires in a circuit have no resistance. So with the switch closed, we've now completed a loop. And because it has no resistance, when the current gets to that junction, all of the current is going to travel down the wire that the switch was on, and none of the current is going to travel down the line that has lamp B. What that means is we have essentially eliminated lamp B. This is a process known as short circuiting, in that we have this wire that eliminates a certain device. Now because of that, we have to think of what's going to happen. Well, when lamp B is eliminated from the circuit, we have essentially decreased the total resistance of the circuit. And because of that decrease in resistance, based on Ohm's law, we know that the only way for that to happen would be to have the total current increase, because we're not changing the voltage of the power supply at all. Well, because of that, with new current across lamp A, we're actually going to increase the power dissipated on lamp A, because we know from our previous studies that power is equal to IV, which is also equal to I squared R. So if we know that the current has increased, we also know then that the voltage drop on the internal resistor has to increase as well. And because more of the EMF is lost to this internal resistor, when you hook up the voltmeter across the terminals, which are the two dots around the power supply and the internal resistor, the resulting measurement will inevitably be lower. Well, everybody, that concludes our lessons on electric circuits. There's a lot of practice problems out there to deal with, so best of luck to you with those, and we'll see you again.